Welcome to Standing on the Shoulder of Giants. This week we're looking at gravitational waves. In February of 2016, an international group of scientists announced one of the most exciting discoveries ever seen in astrophysics. After months of analysis, they had reached a remarkable conclusion. 5 months earlier, two of the world's most sensitive physics experiments in eastern Washington state and southeast Louisiana had detected gravitational waves. Both sites had picked up the fleeting but unmistakable signal of two black holes, 29 and 36 times the mass of our Sun, colliding and merging 1.4 billion light-years away. The cataclysmic event had set off ripples in the fabric of space-time, travelling at the speed of light and arriving at Earth on the morning of September the 14th, 2015. Coincidentally, the discovery came 100 years after the theory of general relativity was published, when Einstein himself predicted the phenomenon, but also despaired at ever detecting it. His theory had demonstrated that gravitational waves should exist, but it also revealed that they would be absurdly minute, seemingly imperceptible disturbances in the fabric of space-time that would surely be impossible to measure with any human-made machine. A century later, decades of effort from an enormous team of scientists and engineers would make the impossible happen. Since the first announcement, gravitational wave astronomy has evolved from groundbreaking to almost commonplace. New detections, once closely guarded secrets, are now announced on social media almost soon after they happen. We have found more pairs of black holes, detecting merging neutron stars, and even begun to spot hints of other, more exotic gravitational phenomena. In just a few years we've already learned a great deal about gravitational waves and the colliding objects that produce them, and we're facing a bright future in this young and exciting field. In this program we'll dig into what gravitational waves are, as well as the workings of the enormous observatories and heroic teams that accomplish the mind-boggling task of detecting them. Gravitational waves are density waves in the fabric of space-time. Remember, space-time is that grid we imagined in our last program, which tied together space and time and bent under the influence of gravity. Bending it was one thing, but making waves in it might sound a bit strange or be a little hard to picture. To understand how these waves work, imagine that you're holding a slinky between your hands. If you look at that slinky, there's two different ways that you can cause a wave. One is the obvious way. You could take the slinky, lift one end, and watch the curved wave propagate from one end to the other. But this isn't quite how gravitational waves work. Gravitational waves are more like compression waves propagating through space-time. If you instead hold the slinky and briefly bring one hand closer to the other, you'll make a different type of wave. This one squeezes and stretches the coils in the slinky as it travels, and this is the best way to imagine a gravitational wave. Gravitational waves travel at the speed of light and squeeze and stretch space-time itself, along with everything in it. This includes our own planet. As a gravitational wave passes through Earth, we'll be squeezed and stretched as well. We learned in our last program about how astronomers could spot the warping of space-time by gravitational lensing caused by stars and galaxies, but these effects are huge. The challenge of detecting gravitational waves is that they're tiny. An epic collision between two black holes, like the one discovered in September of 2015, will generate a squeeze in space-time that's 1,000 times smaller than a proton. Einstein himself described this effect as having a practically vanishing value. Early work on gravitational waves was focused on detecting not the waves themselves, but the energy of the waves. In 1974, two astronomers named Russell Hulse and Joseph Taylor discovered a binary star system composed of two neutron stars. One of these neutron stars was a pulsar, the same type of strange star first discovered by Jocelyn Bell, that emitted perfectly timed pulses of radio emission. By studying this system for years on end, Hulse and Taylor discovered that the binary orbit of these two stars was slowly decaying, with the two neutron stars spiraling closer and closer. This decay meant that the system was losing energy, and the decay agreed perfectly with the predictions of general relativity. The lost energy was most likely being carried away by gravitational waves. It was an immensely exciting discovery, earning Hulse and Taylor a Nobel Prize in 1993. Still, measuring lost energy from the binary system and explaining it with gravitational waves was a bit like seeing smoke and inferring that there was a fire. It was deeply compelling evidence, but some scientists were still dead set on spotting the actual flames. One of these scientists was Joseph Weber. In the 1960s, following a conference that discussed gravitational waves, he set up a series of experiments using enormous aluminium bars. Weber imagined that a gravitational wave passing through one of these bars would squeeze it in one direction, stretch it in another, and set it ringing like a tuning fork struck by a hammer. He fashioned carefully engineered bars, fitted them with detectors that would report this ringing, and placed them far apart. One in his lab at the University of Maryland, another at a golf course 8 miles away, and a third hundreds of miles away in the Argonne lab in Chicago. The bars immediately began ringing, often and occasionally simultaneously, and Weber enthusiastically announced that the simultaneous ringings were being caused by gravitational waves. Unfortunately, other teams began trying to reproduce Weber's results and came up empty-handed. Today we don't believe that Weber was actually capturing gravitational waves, but at the time his experiment sparked a great deal of interest among physicists, wondering if this was a sign that detecting gravitational waves might be possible. The curious physicists included a small group of graduate students at MIT. They were just beginning to study general relativity, and were stymied by how these bars could possibly work, so they brought their questions to their professor, Ray Weiss. Ray Weiss had been born in Berlin 1932, but during his youth his family was forced out of Germany and then Czechoslovakia, eventually settling in New York City. Weiss had attended MIT, struggling through the challenging physics courses and briefly dropping out to work as a technician for Gerald Zacharias. Zacharias was a physicist who developed the first commercial atomic clock, and took a decidedly engineering-based approach to his research, using high-precision measurements to test fundamental principles of physics. Eventually Weiss earned his bachelor's degree and then his PhD from MIT, and after a brief stint of research at Princeton, he returned to MIT as a junior professor in 1964. Asked to teach a general relativity course in 1967, Weiss didn't dare admit that he didn't actually know much about general relativity, and instead scrambled to stay just ahead of his students by learning about experimental tests of gravity as quickly as he could. When his students asked him to explain Weber's strange ringing bar idea, Weiss puzzled over it for a weekend and returned to his class with a thought experiment. Instead of imagining a solid bar, he instead stripped the experiment down to the most basic principles: how gravitational waves affected space-time, and how that effect would be detected by Earth-bound laboratories. Weiss's imagined experiment eventually grew into the gravitational wave detectors used today, based on a deceptively simple principle. Imagine a detector made of two long straight arms set at a right angle to one another and connected by a central building housing a powerful laser that gets split with half the beam sent down each arm. The two arms are precisely the same length, so on a normal day the two laser beams will each travel along the arms, reflect off mirrors placed at the end and come back, travelling exactly same distance and arriving back at the building at precisely the same time. Inside the building, the simultaneous arrival of the two laser beams will be in phase with one another and produce a null signal, showing nothing out of the ordinary. Now imagine doing the same thing when a gravitational wave comes by, compressing space-time in the direction it's travelling and squeezing the one arm of that detector as a result. Now, if you send lasers along both arms, they'll arrive back at the central building out of phase. One laser has taken a slightly shorter trip than the other because of the different effect that the gravitational wave will have on the two arms of the observatory. The result produces a signal that we can detect. Ray Weiss's first detector was a tiny prototype with arms just 1 meter long. Around the same time, a group across the country at Caltech, led by Kip Thorne, had also begun exploring the possibility of detecting gravitational waves. Thorne, in particular, was focused on the theory of gravitational waves, the astrophysical phenomenon that could produce them, and how these gravitational wave signals might appear in a detector. An event like the merger of two black holes generates a brief blast of gravitational waves with increasingly high frequency waves rushing through space-time as the black holes spiral inward. In a gravitational wave detector, these waves will produce a distinctive signal known as a chirp. Because if we translate the frequencies of the gravitational waves into audible waves, it sounds like a chirp. It may sound silly, but detecting that quick swooping note became a key goal of gravitational wave experiments. By the mid-1980s, the MIT and Caltech teams had joined forces and begun developing what would ultimately become the Laser Interferometer Gravitational Wave Observatory, or LIGO. Detectors with arms nearly 2.5 miles long and mirrors hanging at the ends, painstakingly engineered to detect the tiny chirps and other signals of minute density waves in space-time. Today there are two LIGO detectors, one in Hanford, Washington, the other in Livingston, Louisiana. Like the name suggests, the LIGO detectors are interferometers, an instrument that combines multiple sources of light. This may sound familiar. We learned in an earlier program about radio telescope arrays that used interferometry to combine data detected by multiple antennae. The LIGO interferometer takes the same basic principle, recombining light after it has travelled over a distance to measure exactly how far the light itself has travelled and search for disturbances caused by gravitational waves. The concept seemed deceptively simple. Build a detector, turn it on, and wait for the inevitable squeeze and stretch of a gravitational wave. If Einstein is correct, and if the detector has been built properly, it should just be a matter of waiting until two black holes merge somewhere in the universe, and send some waves our way. It's probably true that even back in the early days of LIGO, the detectors were perfectly capable of detecting gravitational waves. The problem was that we were also detecting everything else. A gravitational wave squeezing and stretching a LIGO detector will, at a fundamental level, cause the mirrors in the arms to move slightly and reflect the laser shining down the arms at slightly different times. But think about everything else that could cause the mirrors to move even a little bit. Earthquakes, trucks, falling trees, rain, wind, even footsteps. The real challenge with these detectors became not detecting all of these other extraneous signals, referred to as noise. that could obscure or drown out or mimic the tiny chirps announcing the arrival of a real gravitational wave. Remember, we're talking about detecting something 1,000 times smaller than a proton. Building something sensitive enough to detect subatomic sized compressions of space-time, but robust enough to ride out an earthquake, sounds like an engineering nightmare. These challenges consumed much of the multi-decade effort that went into developing LIGO. The mirrors alone presented enormous difficulties. LIGO's mirrors today weigh about 90 pounds. They're made of pure fused silica glass to reflect the infrared lasers used to measure the LIGO's arm's lengths. Each mirror is suspended on a 4-link pendulum system of thin glass fibers to reduce the outside vibrations that get transmitted to the mirror. Glass was chosen in part because the molecular motion within these fibers as an improvement over what would be seen with metal wires, and this reduces the microscopic vibrations that get passed along to the mirror. The mirrors hang inside enormous vacuum tubes, built so straight they take the curvature of the Earth into account over their nearly 2.5-mile length. The tubes themselves are mounted on an underground slab that helps minimize the effects of wind and seismic activity. Even the ground itself is a potential source of trouble. A tiny seismic wave passing through the Earth's crust will temporarily change the density of the nearby ground, and this in turn would slightly change the gravitational influence the ground has on the mirror. You can probably think for a few minutes and imagine a dozen other potential sources of noise, like logging operations in Louisiana, waves hitting the shore 200 miles away from the Washington detector. If you can think of it, odds are a team of engineers at LIGO have figured out a way to protect the experiment from it. This gives you some sense of the enormous scientific undertaking that LIGO became. Tackling any one of these many noise challenges would involve a sizable team of physicists, engineers, technicians and support staff. Huge research groups were involved in designing every last inch of these immense custom-built detectors. Crews worked for years on making these details a reality, and teams of scientists were constantly testing and retesting and reimagining everything from the glass that made the mirrors to the finer details of general relativity itself. Anyone who's ever worked in a group can appreciate what this meant for the scientific project. In order to succeed, the LIGO project needed to grow dramatically, encompassing and organizing a team of thousands that spanned multiple continents. This crucial expansion happened under the leadership of Barry Barish, a Nebraskan-born physicist who had led the high-energy physics group at Caltech for more than a decade before becoming LIGO's director. Barish's leadership combined immense scientific talent with the equally vital capability of directing LIGO's human and logistical machinery. Barish led LIGO through the thorny and challenging process of getting funding from the National Science Foundation, oversaw the construction and commissioning of the detectors in Washington and Louisiana, and cajoled thousands of people into an international and smoothly functioning scientific collaboration. Crucially, Barish proposed the idea of building LIGO in stages. The initial stage, he knew, would likely not be sensitive enough to detect gravitational waves, but would serve as a vital verification of whether detectors could function properly. The second stage would represent a system-wide upgrade, painstakingly shifting LIGO's operations to more advanced technology that would greatly increase the likelihood of detecting gravitational waves. Skeptics were displeased with the lengthy timeline. Construction began in 1994, and LIGO didn't even begin gathering data in its initial less sensitive state until 2002. It then ran for 3 years, working excellently, but not detecting a single gravitational wave. While this was a notable success for technology, some astronomers had come to see gravitational wave detection as a pipe dream, with Barish's team engaged in a careful but ultimately fruitless search for an undetectable phenomenon. Barish served as LIGO's director until 2006. That year kicked off another painstaking decade of work by what was now an enormous international team, upgrading and testing LIGO in preparation for the second, more advanced stage that would begin gathering gravitational wave data in September of 2015. On the morning of September 14, 2015, LIGO wasn't quite up and running. At least, not really. The LIGO detectors had been tested for years as part of the advanced upgrades, and that morning the detectors were in a phase known as an engineering run, operating and gathering data as part of the final test, with a few auxiliary systems still offline. One of these systems, known as the blind injector, had proven to be a small but crucial part of LIGO's operations in previous years. Early on in the project's development, a handful of team members had been given an unusual task. They were asked to occasionally inject fake signals designed to look like gravitational waves into the data coming from the detectors. These injectors wound up testing the noise of detectors as well as the noise of the people that made up the LIGO collaboration. If a detector failed to catch one of these signals, it was a clear sign that the technology still needed work. If a signal was detected, the challenge became how the team responded. LIGO team members knew that fake signals could be injected into the data, but they also knew that LIGO might at any moment capture the real thing, and the work of the blind injection team was true to its name, hidden from the rest of the collaboration. Because of this, any signal that appeared in the data had to be treated as real. Team members would analyze the signal's data, work through the math and physics to determine what might have produced it, and even draft a research paper announcing the result. The work would culminate in a final team-wide meeting where the blind injection team would be called forth to report on their work. Then, and only then, would the LIGO scientists find out if they had been working on an injected signal or a real detection. This process also had an interesting side effect of testing team members' ability to keep a secret. The detection of gravitational waves was universally seen as one of the greatest potential discoveries in modern physics, and any preliminary data would need to be treated with great care and secrecy. Nobody wanted to convene the world's press and triumphantly announce a result that later turned out to be a mistake. As a result, the blind injections would also test the LIGO team's poker faces, ensuring that nobody would leak news of a potential discovery until it was certain. The system had worked incredibly well during the earlier phases of the project, testing the detectors with occasional fake chirps, simulating colliding black holes, and keeping the team on their toes. So far, every chirp that had been detected by LIGO and met with excitement by the team of collaborators had come from the blind injector. However, on the morning of September 14, 2015, the blind injector was off. Team members had been tinkering with the system's collaboration just the night before, preparing for the first official observation of LIGO's advanced stage, but had left it off as part of LIGO's final engineering tests. This meant when an immense chirp from two merging black holes appeared in the data, several LIGO scientists immediately knew that it might be the real thing. The data were carefully scrutinized. The team even considered the possibility of what they called a malicious injection, a faked signal secretly inserted by someone outside the blind injection team, or even someone outside the collaboration. But eventually months of careful analysis and tests were complete. The September 14th chirp was real. LIGO had detected the first gravitational waves. The announcement was met with worldwide fanfare and acclaim, and earned Weiss, Thorne and Barish an immediate Nobel Prize in Physics. Notably, the prize's recognition of Barry Barish gave a clear nod to his incredible work on masterminding the scientific growth of the collaboration. The discovery had not been achieved by 3 Nobel laureates working alone, but by the combined efforts of thousands of scientific heroes working one of the longest and most complicated physics experiments in history. Decades of determination and dedication and groundbreaking engineering work by this team had finally succeeded, ushering in a new era of astronomy. Since that first discovery in 2015, LIGO has continued to successfully detect gravitational waves, finding more merging black holes, and even picking up the first signs of other rarer phenomena. In August of 2017, LIGO made another groundbreaking discovery, detecting the longer chirp of 2 merging neutron stars. That chirp appeared in the Louisiana data first, and in the Washington detector 3 milliseconds later, revealing that it had come from somewhere in the southern hemisphere. 1.7 seconds later, a space telescope detected a telltale quick burst of gamma rays from the same part of the sky, something that hadn't been possible with previous discoveries, since no light is emitted by colliding black holes. Astronomers had previously predicted that merging neutron stars could produce something called a kilonova, an extremely bright and brief flash of light observable across the entire electromagnetic spectrum, and that this gamma ray burst was the earliest signature of such an event. Immediately, observers all over the world scrambled to point over 70 of the planet's biggest telescopes at the patch of sky where the neutron star merger had happened, and they soon spotted the light of the kilonova in a nearby galaxy. This meant that, for the first time, astronomers could combine electromagnetic light and gravitational waves from a single event, gaining a new and rich combination of observations for studying stars, space and gravity. We've just explored how gravitational waves are detected, but how did astronomers spot the telltale flash of the kilonova? The sky is immense, after all, and we know from the study of supernova that finding a tiny change like a newly appearing spot of light can be challenging. In our next program we'll examine this detail of our energetic universe, exploring how astronomers survey and study the constant subtle changes happening in the night sky. Well, time has caught up with us again. Time to move over and let someone else have a go as usual. I'll be back next week with more tales from Standing on the Shoulder of Giants. Please, everybody stay safe. There's still a COVID jungle out there. Look after one another, and I'll see you next week. Bye for now.